We're going to get started, guys. So hope you guys are having a great event so far. Now we're in our breakout sessions. So there are two sessions happening in parallel right now at the same time. So the one up here and the one downstairs. You've got the bios of the speakers and what they're going to be talking on. So we'll just get straight into our first talk. I'd like to introduce to you guys Katarina Ilic. She is from the class of 2013 for the Nanotechnology Engineering program, and she leads the research and development aspect of Voltera. So a lot of you probably know Voltera. It's been a great hit in Waterloo and around the world, and they've won the Dyson Award. So she's got a great story to tell you guys about her transition from the Nano program and getting into Voltera and the story of how Voltera came to be. So just a little bit more background on Katarina. In her internships and co-ops, she's been working in IBM Germany, EPFL, which is a university in Switzerland. So a lot of research background and a unique perspective from the startup, a successful startup company. So without further ado, I'd like to welcome Katarina Ilic.
Thanks a lot. Can you guys hear me okay? Is this thing working? Yeah? It's okay? Okay. First of all, thank you all very much for being here. It's actually very nostalgic for me because I remember being in this exact classroom about 3.5 years ago. And where you're sitting right now was my spot. That was exactly my spot where I'd come and sit every single day. And so it's very nostalgic for me actually to be back here. I haven't been back on the university campus for a very long time. And I guess a little bit of a background for me actually. As soon as I graduated from nanotechnology, I did the specialization in bio-nanomedicine. Do they still have that? Yeah. So I did that, and then I was actually on my way to Switzerland at a school called EPFL, called Polytechnique de Fédérale. And there they have a very large material science school, which I spent about 2 years in preparation for. I did my 8-month co-op there, went through the entire jarring 8-phase interview process. Got accepted to EPFL, and then little did I know that it was on that very, very last day, actually, the day that I wrote my last exam, that basically everything was going to change. And what I thought I wanted wasn't actually what I wanted at all. And so that very last day, I found myself talking to a good friend of mine, Jesus, now my co-founder. And he was telling me, you know, they were doing this capstone project in engineering where they wanted to bring additive manufacturing and rapid prototyping to circuitry, to electronics. Only they were missing this chemical aspect, this material science aspect that they very much needed in order to succeed. And so I said, okay, Jesus, you're a good friend of mine. I'll help you guys out for the summer. And meanwhile, the summer is slowly passing, and I'm very much in denial about the fact that I'll be turning down my PhD offer that I was preparing for in 2 years. And I literally waited until the very last day until I said, I can't believe I'm doing this. But I called up my professor in Switzerland and I explained to him the situation. And I said, I'm not coming. I'm not coming. Instead, me and my 3 guys, my 3 co-founders, we scraped together as much money as we could, and we moved into a garage to attempt to do what many, many experts told us was actually impossible from a material science perspective. And so what exactly was that? Well, I'm here to talk to you today about hardware primarily, because hardware is integrated in every single aspect of our lives, from your cell phones to your laptops to your TVs. You know, you can't really go anywhere without hearing about the next smartphone, smart car, smart wearable something. It's really integrated in every single part of our lives. The only thing is that developing hardware, I have to tell you, really, really sucks. And that's because it all starts with the circuit board. When you're iterating on hardware, you have to actually build physical product. It's not like building a code. It's not like building software where you can just see if your program works at the click of a button. You have to build physical product, and you have to iterate on it. And so we slowly watched as 3D printing was solving this problem from one aspect. So this was the time during the maker movement, right? You had this beautiful technology come into basically front and center screen, where for the first time now, developers, they were able to rapidly prototype these plastic mechanical structures. So you can go from a CAD on your screen to actually having a physical product within a matter of hours, which was absolutely fantastic. only there was still that aspect missing of being able to rapidly prototype electronically functional devices. And so basically, you had two options, which we were stuck with. One, you could outsource your circuit boards to facilities just like this one in China. This is actually one of the factories that we work with in China. And basically, you'd be stuck sending your files over across seas, waiting 3 weeks to get them back, paying minimum order quantities of 500 boards when you just need one for prototyping, just to get it back and find out another iteration is required. And so goes the process on and on until your design is actually finalized. And you can imagine, especially when you're a small company with a very, very limited runway, agility is the only advantage that you have over larger corporations. So you have to move quickly. You don't have time to essentially be losing all these opportunity costs waiting on factories like this one. So your other option is to chemically etch the boards yourself. Has anybody here actually done chemical etching of a circuit board? Raise your hands. Okay, so a few people are familiar with the process. It looks something like this, okay? It's essentially photolithography, and you start off with basically a copper-clad board, and then using UV light and using really, really nasty chemicals like ferric chloride, you etch away that copper. It's subtractive manufacturing technology, where you etch away that copper so you're left with your circuit board at the end of the day. Now, early on when we were actually developing our product, we had to do exactly this process in order to create the electronics that are actually embedded in the tool itself right now. And so these chemicals are so nasty to work with that I remember we were working out of the Voltera Garage, and after hours, we would take a table, after hours at 5 p.m., we would take a table, we would drag it into the handicap washroom, and this is where I did all of my chemical testing. This is how I etched my circuit boards. I remember one day we had a nasty spill of ferric chloride all over the floor. And to this day, this bathroom still looks like a murder scene in there because it just completely stained everything. And there was just no cleaning it up after that. But this is what we were left doing. And we said, you know, we've had enough. We need to be able to move faster without dealing with nasty chemicals like this. And it was funny because as we were doing this, we were thinking, this is exactly the problem that we want to solve, a convenient way for actually being able to prototype circuitry. So we actually picked up and we went off to China. And this, we moved to Shenzhen. Shenzhen is actually the electronics manufacturing capital of the world, okay? About 85% of electronics come off of the ports of Shenzhen. So imagine that, 85%, everything from Apple products to Sony products, Samsung products, all come off of those ports, okay? What does that mean for us? That we were able to move really, really fast there because they actually have the infrastructure built up to be able to rapidly prototype physical products and electronic products. So we moved to China and we built our industrial design there. And when we came back home, after being in multiple factories like this one, for example, this is my co-founder Jesus, working with some of our colleagues in China. This is actually our circuit board factory that actually produces our control boards right now. And so we picked up, we went home, and when we got home, we came back with this, the Voltera V1. An additive manufacturing technology, a rapid prototyping tool for circuit boards that essentially allows you to just design your circuitry in whatever software you're already comfortable with, whether it's Eagle, Altium, KiCad, just press print, and within about half an hour, you have a fully functional circuit board that's ready to be prototyped. So I'm going to show you our little trailer video. It's a lot easier when you actually see it in action. So it dispenses a silver nanoparticle-based conductive ink on the substrate, lays down the traces and the pads. And after that, the platform of the printer will actually thermally cure them. Even past that stage, it'll actually dispense the solder paste for you so that you could actually attach functional components onto your circuit board. And even after that, it'll reflow them for you. So at the end of the day, you actually have something that's electronically functional. Okay, so that all really happened very, very fast. So let's slow down a little bit, take a step back and find out how this actually works. So the secret sauce of the Voltera V1 actually is stemmed in nanotechnology, okay? It's in a conductive silver nanoparticle-based ink that took about 1.5 years of development time. So it's a solution that's in here. I know it doesn't look like much right now, okay? There was a lot of sweat and blood that went into this, believe me. It's about 95% silver nanoparticles, about 5% different polymers, different types of additives. And so essentially, it dispenses this silver nanoparticle paste as the traces in the pads of your circuit board. And then after that, the platform of the tool is actually a thermal bed. So it'll go ahead, it'll heat up, it'll thermally cure that conductive paste. So you have cross-linking happening right now. Remember that word, cross-linking? I learned it here. And so at the end of the day, once all the solvent has evaporated, you essentially have these solid silver traces that are fully conductive and fully electrically functional. And so this is an SEM image that I actually took here at the University of Waterloo, giving us a bit of a closer look of what that actually looks like on the nanoscale. So you can see the scale here is about 200 nanometers. Each of those particles are about 50 nanometers in diameter, with a bit of a distribution there. But essentially what's happening down at the nanoscale is as soon as you have this thermal action happening, all of these nanoparticles that were suspended in solution actually come together and they form what's called a silver nanoparticle matrix. And so you have the contact of all of these silver nanoparticles that electrons can then essentially run through, and so you can have conductive properties coming out of it. And so you can go ahead and just build stuff. For example, I mean, this is just something very simple that we just created. One of our students in our office, he created the game of life. So look what you have actually happening there. I mean, these are just some LEDs lighting up, but you actually have full electrical performance that came from a tube of ink. And that is something that's actually very, very incredible. But on top of that, we have users from everywhere that are using it from all kinds of various applications that you just simply couldn't do before. So for example, printing on various types of substrates, printing on glass, printing on flexible electronics. This is a radio frequency antenna that was printed on Kapton. This is simply something that was not able to be done before, the ability to rapidly prototype electronics on flexible substrates like this one. This, for example, is a radio frequency antenna that we had a user print at the Southern Alberta Institute of Technology. So he actually created his circuitry. I believe it was done in Altium. He went ahead, he had it printed within about 20 minutes. It was complete, and he was actually able to test its radio frequency properties. And I believe this particular antenna functioned at about 400 gigahertz, which is actually quite amazing. I mean, even I was surprised that it can function at such a frequency, given the fact that it is silver nano ink. So the potential that this technology has to accelerate innovation has really been recognized on a global stage. We've received the Popular Science Award in 2015, Top Invention of the Year, the James Dyson Award for Design and Engineering, Hardware Battlefield. My favorite, just because I love Maker Faire, was their Editor's Choice, among others. And so this gets me really, really excited, because as soon as actually this happened, we had this enormous, basically, media push. And then suddenly we had people from all around the world that were finding out about us and that were coming to us. And we said, you know, we were first very, very overwhelmed by the amount of orders that were actually coming in. And we said, okay, well, I guess we're going back to China now to get some elementary parts built. However, the majority of the manufacturing was actually done here, locally. And so we started building the Voltera V1 at our in-house facility. It's actually just here in Kitchener-Waterloo. This is a part of my team. And so it's fully assembled, fully calibrated, fully tested at our in-house facility. And from there, it's shipped to the rest of the world. And here are just a few of our customers. So what we found really, really incredible was the fact that all of these people, they were coming from just all different aspects of life. They were coming from the academic sector, small businesses and large businesses. They were coming from the hobbyist sector and from the maker sector, really just from absolutely everywhere. And it really kind of verified the fact that this need to rapidly prototype circuitry has actually been missing for all of these people for quite some time. Our most recent larger company to add to this list is actually Apple. They recently bought some units. But what was even more amazing to me is just everywhere that it was actually going. I think I mentioned I was looking over some of our sales, and I noticed that 50% of them were actually coming internationally. This was a bit of a surprise to me because when we first started this thing, it was actually meant to be kind of a tool for the West, you know, for Silicon Valley, for California, you know, all these people that are known to be very, very innovative sectors and makers. But then we started getting inquiries from everywhere, including some very strange places, actually, such as the DR Congo and Sudan, you know, and really just absolutely all throughout the Middle East, all throughout Africa. And there were so many maker spaces that were coming, people coming from the educational sector. They wanted to use this thing to teach their students, and just small startups like ourselves that just needed a tool to be able to rapidly innovate without having large manufacturing facilities on the other side of the planet interfere with their development time. And this is what got me tremendously excited. Not even so much to see, you know, what Silicon Valley is going to do with this thing. As I said, there's only so much wearable tech one could make, right? But just to really see what all of these places are going to do and to see the types of products that they're going to produce with the Voltera V1. And to me, this is something incredibly important because I think if one thing's been shown throughout Western history, actually, it's that innovation actually gives you a tremendous competitive advantage over the global market. And so if we can give people in other parts of the world this ability to rapidly bring their products to life, perhaps we can help give them that competitive advantage as well. And I put here from Silicon Valley to Amish country and beyond, because I got kind of a nice story there. This happened actually a few weeks ago, where I'm sitting in the office and we get a phone call, you know, and somebody they want a demo essentially, which is nothing new. We get, you know, requests for demos all the time. So I say, sure, absolutely, you know, are we free next week to come in for a demo? And they say, oh, okay, well, how about now? And I'm like, okay, I guess I'll cancel my 2 o'clock meeting now. It works too. Okay, great, we're on our way. We're 20 minutes away. Okay. And I remember, you know, they give me a call when they get there, and they're, oh, we're here, we're waiting in the front lobby. So I was like, okay. So I go out to the front lobby, and I remember like standing, and like I'm looking around, and there's these 3 older Amish gentlemen that are just standing there. And I stood there, and I'm kind of looking at them, and they're kind of looking at me, and I'm like, no, these can't be the guys. And they're like, Voltera? And I'm like, yeah, you're here for the demo? Yeah, okay, great, you know. So I bring them into the office, we give them the demo, they absolutely loved it. They say, we need this right now. And I remember they said, you know, can we take this one? Can we just take this one? You know, we have the money right now, we can just give it to you. And I'm like, oh, I'm sorry, gentlemen, you actually have to wait your turn. There is a bit of a lead time, you know, 3 weeks. And they're like, oh, okay, well, put us in the line. And I had to ask, I was like, so what do you gentlemen want to use this for? And so there are 3 engineers that are operating out of St. Jacobs. And they have this little workshop, and they're saying that they're developing this little incubator for making maple syrup. And I mean, I didn't know this, but apparently the production of maple syrup is a very, very temperature sensitive process. You have to very carefully, you're nodding your head as if like, I know everything about maple. So yeah, I can see that. You're like, oh, I know everything about that. So there you go. So now they want to build essentially this incubator that can very carefully monitor the temperature of their maple syrup so that they can get the highest quality maple syrup and then sell it. And that just made me so happy that hearing applications like this, you know, and they said, we're so stunted, our development is so stunted because we're just waiting for circuit boards to come in all the time, and we need to move quicker, we need this. And see, things like this get me very, very excited to see what people would use this for that's not as conventional as you may think. But okay, apart from accelerating development, there's a few other reasons that additive manufacturing can be very beneficial to our society in general. this is a photo of a landslide that actually happened in Shenzhen. Now, this actually happened last year while I was in Shenzhen. It actually happened just a few miles out from where I was living. And so what happened here is you had this enormous landslide that took out 85 buildings, nearly 100 people were unaccounted for. And this actually happened in kind of the manufacturing sector, and it was a direct consequence of waste basically produced by subtractive manufacturing. Okay, so you have all of these factories that are using all these subtractive manufacturing techniques. That same etching procedure that I talked about, you know, that's the exact same procedure that these factories are using, except on a mass scale, okay? So that little ferric chloride spill that I talked about in the bathroom, imagine that happening in gallons, in the tons. And essentially, you have improper waste disposal that happens, and it degrades the soil. And that's exactly what happened here. It was the degradation of the soil that essentially caused this mass landslide to happen. And now we're just scraping the surface of additive manufacturing technologies. But if we can project this into the future, if we can keep going down this path of additive manufacturing, imagine only use the material that we actually need for our products. No waste, much better for the environment, much better for people in general. I'm going to read you a quote here that came from Howard J. Brown, his paper. He's a famous researcher in this area, and he says, these technologies, referring to additive, have almost unimaginable potential to generate wealth with fewer overall tons of waste per capita or production unit, thus drastically extending the life of our available resources. There is no question that their continued development is the only way to expand prosperity for a growing population, given an intensifying resource supply problem. And so what he says couldn't be more true. So as I mentioned, we're just kind of the pioneers in this industry, you know, but hopefully I kind of see a future where in 30 years from now, we can remove subtractive manufacturing altogether and just live in a healthier world. And so now, let's take a step back here. If I was, you know, back when we first started this project and I was kind of, you know, the original chemist, and I was just kind of, you know, in that bathroom etching those circuit boards with just my co-founders, I actually never imagined that we'd be tackling a problem of this magnitude. And what I kind of realize now that I didn't realize at the time is that a nanoparticle can actually solve a giga problem. So this doesn't, you know, this isn't necessarily just about getting circuit boards fast enough, right? As I mentioned, it's just scraping the surface of this movement. Only I could hope that will eventually, you know, lead to a better world with additive manufacturing techniques. This is my team here, which I always have to acknowledge at the end of every single talk, because these are all incredibly brilliant people that are all way smarter than me, and I have each and every single one of them to thank. Amanda here on the far left side there, she's actually a co-op student from the University of Waterloo, and we're always accepting applications as well, so feel free to apply. And I think that's about it. Okay. If there's any questions, please feel free.
Thanks, Katarina, for that great talk. And we're running a little short on time, so we're going to go with, say, 2 questions. And before we do that, I'm just going to introduce the talk that's going to be happening in the floor below, so just so that you guys have an idea of what's coming up. So Elizabeth Salzberg, she's a master's student, and she's going to be giving a talk on organic photovoltaics. So just letting you know in case you want to switch rooms. So first question, I'm going to have to bring the mic up to you. Yeah? Here, we'll just pass it down through here.
My question is, because you were kind of vague about it, but like, what if like all the people who want your product all buy it? What are you gonna do afterwards? How are you gonna, like, what if everybody already has it then? You know what I mean? Like, what is your next, like,
What's our next step?
Yeah.
Oh, there's still much, much more to do. As I mentioned, we're only scraping the surface of these additive manufacturing technologies. But if you want like kind of a vision of the future, you know, imagine that you can be in a situation where basically you can have these additive manufacturing machines that are not only depositing conductive material, they're depositing plastics, they're depositing metal, as we see in many different technologies right now. And if you could actually integrate all of these things, you could essentially create entire physical products. I mean, this is 20 years down the future, but imagine you can actually create, you know, phones, laptops, all through additive manufacturing technologies. As for the next step for us personally, Voltera, one step at a time, right? We're going to be looking into making hopefully another version of the V1. This one still, it can definitely use a lot of improvement, and there's a lot of features that are very commonly requested by our customers. So first step is catering to their needs.
One more quick question, if anyone's got any. Yeah, we've got one in the back. Just coming up. We need to use the microphone to get you on audio for the video, for the camera.
Like you said that customers need a lot of stuff. What is the most requested feature that's not part of the V1 that customers want?
Oh, they want everything. They want it to make their breakfast in the morning. The most commonly requested feature, I would say, is a pick-and-place system. So as soon as you're essentially finished creating the circuit board, it actually has to go ahead and dispense a material called solder paste that actually creates the joint between the electrical components and the actual the traces themselves. And then after that, you have to place the components. Now, this machine, you're actually limited to placing the components manually. And then after that, the machine will reflow them for you, which means attaching the components to the actual traces. However, we have, this is an interchangeable printhead apparatus that we have a published patent on. And this is actually very, very powerful because it allows you to interchange not only different printheads and different materials to dispense, but also different types of tools. So hopefully that'll be the next thing to work towards, you know, making our customers happy, creating some sort of attachment that allows them to automatically, completely just eliminate the process of manually placing components.
Cool. We're really short on time, so we're going to...
We can talk after.
Well, yeah, we're going to end it here. I'd like to thank Katarina once again for taking the time to come and tell her story about her life beyond Nano and how it was put together by Nano. So we've got a small gift for her, the classic Waterloo Canada Goose.
Is it a real one?
It's not real.